Welcome to problem solving session for linear algebra. Today I'm Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 9, that is problems related to complex vector spaces, inner product space, inner product and length, and orthogonality. So let us start. So my first question is, which of the following are inner product spaces with respect to the given inner product on V cross V? Okay, so they are asking, so we'll be writing few maps from V cross V to given base field, and we will have to check which of the following are inner product spaces. So before going to the questions itself, let us start with what is inner product space. So let V be a vector space over F. So F is any base field, and inner product on V is a map from V cross V. So it is map V cross V to F, which satisfy certain condition. First one is linearity in first variable. So when we say that, what this means, that if V1, V2 and W are in V, then V1 plus V2 comma W is equal to V1 plus W, V1 comma W plus V2 comma W. And if C is in my base field and V is in V, or V comma W in V, then CV comma W becomes C into V comma W. Okay, so this is linearity in first variable. So we are considering, it is satisfying the linearity of addition and scalar multiplication in the first variable. And second is conjugate symmetry. So second is conjugate symmetry. Means that if V comma W in V, then V comma W is conjugate of W comma V. So note that if R is, if F is set field of real numbers, then this conjugate is same. So if F is R, then this conjugate symmetry becomes actually symmetry, that VW is equal to inner product of V comma W is equal to inner product of W comma V. So, and third one is that positivity. Positivity means if V belongs to V and V non-zero, then V comma V is greater than 0, or yeah, V comma V is positive real number. Okay, so these are three conditions which a inner product space must satisfy. Okay, so when a vector space has this map with it satisfying these three conditions, then that vector space is called inner product space. Is it okay? And please understand that this linearity in first variable actually, and this conjugate symmetry actually gives us conjugate linearity in second variable. So what that means is that if I have this, so let v1 comma or v comma w1 comma w2 be in v, then if I take this, I mean this is discussed in the lecture, but I'm just reviewing it again. So which is what? W1 comma v plus w2 comma v, which is this. So addition splits nicely, but when we have scalar multiplication in the second variable, then it becomes, so let v comma w in v and c be in our field, then be in our field, then v comma cw is now what? C comma cw comma v conjugate. And now it is cw comma v conjugate, but then it is what? C conjugate into w comma v conjugate, and which is v comma w. So when we take out scalar from the second coordinate, then it becomes conjugate. Note that when we have real, then that doesn't happen because this conjugate again becomes a number itself. So for a in R, note that a conjugate is a itself. So in that case, that's why this linearity in second variable follows as it is in case of R. So this I told, I mean the second coordinate, because it becomes handy when we do calculations. So that's why. So I hope this is clear for now. So let us start with our actual questions. So consider the complex variable, complex vector space. Please let me know if there anything is unclear. You can write it in the chat or unmute yourself and ask. And we define this that x1 comma, okay, it is C2, x1 comma x2, y1 comma y2 is x1 y1 minus x2 y2. Okay, then we have to check whether this is inner product space over C. Complex vector space. So we have to check this C2 is inner product space over C or not. So what is your guess? So note that here we have minus. So best way to think about it is, so if we can prove, then that's okay. But we have this positivity here. So if I have any inner product, then its inner product with itself must be some positive real number. Okay, so if I take, so let this 0 comma 1 in C2. Okay, then its inner product with itself will be what? 0 into 0 minus 1 into 1, or 1 into 1. So which is what? Minus 1. So which is less than 0. So this contradicts the third condition, the positivity condition for inner product space. So that's why this is not, I mean, this inner product space does not, I mean, this map does not form inner product over C. Is it okay?
Ma'am, whether the example you have taken is real, whether real
I mean,
numbers also in
reals
complex.
are inside complex, right? I mean, so that shouldn't.
Okay, understood.
Yeah. Hmm. So reals are always inside complex. So we don't have to go to reals, I mean complex, if reals are itself giving us counter example. Yeah. Still, let me write this. Okay. So is this clear now?
Yes, ma'am, clear.
Yeah. Okay. So let us move next. Is consider R as a vector space over itself. So now R is vector space over itself, and we define this map x comma y going to x into y. And now we have to check whether this is inner product over R or not. This was false. So R over R and inner product is this. And any guesses whether we can find any counter example or this is inner product space? Any guess?
This is true as per definition of R.
Yes, yes, yes. So this is true. So let us try to prove all the conditions of inner product space, because this is, so first let x, y, z in R, and this A in R where I am consider it as field, I mean the base field. Then this x plus y comma z is what? X plus y into z, which is xz plus yz, because addition splits in real number. So then it becomes x comma z plus y comma z by the definition of given map. And similarly, if I take this A into x comma y, then it is what? Ax into y. Then I can simply write this and then it becomes x comma y. So linearity is okay. And now second condition is let me write this here. X comma y is xy, but real number is the multiplication is commutative. So this becomes y into x, which is yx. So symmetry is satisfied. And third is let 0 non-zero x be in R, then x comma x is x into x, which is x square. And we know for non-zero x, it is always positive. Okay, so that's why it satisfies all the three conditions, the linearity and the linearity here in first, the symmetry and conjugate symmetry, and third is the positivity. So conjugate symmetry is just symmetry here because we are over R. So that's why this forms inner product space. Any doubts here? Okay, so just move to next question then. Consider the vector space V is equal to P01, the vector space over R of polynomial functions on 0, 1 with real coefficients. So this is given. And for f comma g in V, they define the inner product or the map, not the inner product, the map to be this. Integration 0 to 1 f dash t g of t dt. Okay, and they are asking whether this is where, okay, let me write this, where f dash is derivative of f. Okay, so this is the given map. F comma g going to integration f dash t into g dash, not g dash, only gt, and that's it. They are integrating f dash t and gt over 0 to 1. And any guesses whether this will be inner product space? Okay, so note that here when we are given this inner this function or this map, the first coordinate and second coordinate are kind of have different. Sorry, the first
So
one
suppose
we are taking derivative, and the second one remains as it is. Yes, sir, you are saying something.
suppose f and g is taken minus x,
F is equal to g is equal to minus x. Okay.
then inner part gives minus negative value.
Then it becomes, how it becomes minus? Because then inner product of f comma f, then you are saying you are talking about the positivity factor, right? But in that case, it becomes f dash is minus 1, g is minus x, so which is integration 0 to 1 x dx, and it is very well, I mean, positive.
Okay.
Hmm. So note that symmetry won't be a problem here. The thing is, sorry, positivity may be problem. I mean, you can always have a function which will give you negative value and so on. That's not a case. But here, note that f dash, we are taking differentiation, I mean, derivative of f, and is as it is. So the problem might occur at a symmetry level because f dash into g need not be equal to g dash into f, right? And when we integrate, then they might yield different problem. So different values. So we have to then choose f and g smartly. I mean, when we try to find a counter example, we need to smartly see like which property would be easy to find a counter example for. Okay, so since f dash into g, we know that it need not be equal to g dash into f. So we will start with that. So any guesses for that? What f and g we should choose so that,
F is equal to 1, g is equal
okay,
to x.
f is equal to 1 and g is equal to x. So let us do this and see what happens. So f comma g will be integration 0 into x, right? Dx 0 to 1, and this is 0, but I mean, this g comma f is what? Integration
Not
0 to 1 dx, which is 1. So clearly this f comma g is not equal to g comma f. So that's why, therefore, symmetry does not hold, or conjugate symmetry, since we are in reals anyway. So, but still, let me write conjugate symmetry does not hold. This not needed, but still does not hold. So that's why this is not inner product space. Okay. Any doubts? Okay, so I assume there are no doubts. Then let us move ahead. So third one, like consider now we are again to real vector space. V is equal to MNR. So set of all n cross n real matrices, and we define A comma B to be trace of B transpose A. Okay, where this BT is transpose of B. Okay, so what is your guess? Whether this will form inner product space. I mean, the map is given to be trace of B transpose A. So B transpose A will again be a n cross n matrix. So they are saying that we will be taking trace of it. So any guess whether this map will give us inner product on space of n cross n matrices? Oops. Here.
Yes, it should, because
Yeah.
it's as per the definition trace of BA.
Yes. Yes. So let us prove this quickly. Let ABC be in R and MNR, and let us take D to be a real number. I mean the scalar from R. Then for did we check scalar multiplication? Okay, yeah, we checked. So if we take this inner product of A plus or evaluate this map on this, then it becomes what? Trace of A plus B into C. But this is true. This is just matrix of transpose, B transpose. Okay, this is true. And then this become trace is additive. A transpose C plus B transpose C. So this is trace of, did I make any mistake? Yes, I did. It is C transpose A plus B. The definition, by definition. Then this becomes C transpose A plus C transpose B, and then this is C transpose A plus trace of C transpose into B, which is trace of A comma C, trace of B comma, oops, A comma C, B comma C, inner product. Is it clear? So C transpose, so multiplication splits over addition for matrices. So that's why this C transpose A plus B becomes C transpose A plus C transpose B, and trace is additive. Because addition of matrices is entry wise, and when we take trace, it is just addition in the this ith entry. So that's why trace is additive, and we get this. The addition and now the scalar multiplication. This dA comma B will be trace of B transpose dA. So note that this dA is nothing but all the entries of A are multiplied by D. Okay, so for this matrix B transpose dA, all the entries will be like multiplied by A. So this becomes now trace of D into trace of B transpose A. And now then this becomes D into A comma B. This we can check. Okay, let me show you this. A, B, C, D. And if this is C, E, not C, E, let me take, suppose T, E, T, E, F, G, H. Then everything like this becomes T, A, E plus T, B, G, T, C, E plus T, D, G. And similarly here, everything will be multiplied by T. And so if I take this T common from everything, then this is just A into B, AE plus BG, CE plus DG, and here it will be second coordinate, the second column and so on. So which is nothing but T into A into B. So that's what I did here. So we can take the T to be common, and if I am just talking about the trace of this matrix, then trace will be this T into everything, and this T if I take common, then it becomes T into trace of this matrix AB. I hope I'm making myself clear here what is happening. Okay, so you can just verify this by numbers or just 2 cross 2 matrix example that this hold here, okay? And the second is symmetry. A comma B is equal to trace of B transpose A, and which is trace of. So one thing we know that trace of A is equal to trace of A transpose. Okay, and for multiplication, AB transpose is B transpose A transpose. So this thing becomes now then A comma B becomes trace of B transpose A, but now I know that trace of this is equal to trace of B transpose A whole transpose. But by this I get this that A transpose B transpose becomes B, and this is what by definition BA. Is it okay? We are just using these two properties to get this. And third one is positivity. So let A be non-zero matrix. Then what is A comma A? Please let me know if anything is unclear. Okay, this is what trace of A transpose A. And what is this? So let me write this. This is as trace of A transpose. So if A is this, A11, A12, A13, so on, A1n, this is AN1, AN2, ANN. If A is this, then A transpose will be what? We are just writing columns as rows, right? So A11, A21, and here it will be AN1. And here it will be A1n, A2n, so on, ANN. Right? And this, so on. So if I multiply this, so when I want trace, I only care about the ith entry, the 1, 1, 2, 2, 3, 3, the diagonal entries of a matrix. Okay. So I will just evaluate those entries and not the others. So then how this will look like? That the new matrix, it will be of this form, right? So first is A11 square plus A21. So here it is A21, right? A21 square plus so on up to AN1 square. What will be the second entry? Second row into second column. But second row is what? Here it is A12, A22, so on AN2. Then it becomes second entry, 22th entry, A12 square plus A22 square, so on up to AN2 square. And it will go on like this. And the last entry, the n comma nth entry will be A1n square, A2n square, and so on up to ANN square. Let me write. Then trace is what? It is summation of everything. It is summation of Aij square I comma j from 1 to n. So it is A11 square, A21 square, A3n, so on. So it is summation of squares of all the entries in first column of A. Second entry here, 2-tooth entry, is summation of square of all the entries in second column. So on n comma nth entry is square of entries in the nth column of matrix A. So this is summation of essentially all the elements of all the entries of matrix A. So then this has to be greater than 0 because A is non-zero matrix, right? So at least one entry. So there exists I comma j in n, I comma j in n comma n, or how to write this? I comma j such that Aij is non-zero. So therefore Aij square is greater than 0. So this whole summation becomes greater than 0 because at least we have started with A non-zero. So note that this is not only, this, let me just write this, that trace of A transpose A is always summation of Aij square I comma j from 1 to n comma m, where A is Aij n comma m. So even for n cross m matrix, it need not be square matrix. For any given matrix, this always holds. The trace is sum of all the entry. Square and then adding this all the entries. Is it okay?
Ma'am,
Yes.
suppose AIG are complex numbers, it will not work.
No, because square could be negative in that case.
Yes.
For example, if I take I in one entry and the rest are 0, then square will be minus. So yes, since we are talking about real vector space, that's why it becoming true here. Is it okay? The rest will be okay. Even for case of complex, the symmetry and everything, conjugate symmetry and linearity. But yeah, the positivity would not work in case of complex numbers. Is it okay? Is there any doubt how this happened here? How the summation of entries came? You can just try this for 2 cross 2 matrix and it will be very clear to you, like how this is happening. Okay. So this is therefore, this map forms inner product space over R. If anything is unclear, please let me know. And we are moving to then now fourth, that consider the real vector space V is equal to M and R. So again, it is n cross n matrices. And now we define this map to be A comma B going to trace of A plus B. And now what is your guess?
No, because it may fail positivity.
Yes, yes. Can you give me a counter example?
Maybe B equals to minus.
Just take diagonal with all negative entries. Uh, I mean, yeah. So addition will be still, so let us without any problem. If we take then B comma B will be trace of B plus B. Okay, then it becomes trace of, since it is diagonal, it is becoming minus 2, so on minus 2. Then it is what? Minus 2n. So it is less than 0, therefore positivity fails. So this -1 was not any special. I mean, you can take anything such that the overall addition of trace becomes negative. And since we are adding negative numbers, it would still remain negative. Any doubts here?
Ma'am, for these questions, whether n into n we can take 1 into 1 also we should consider.
1 into 1 means,
mean,
sir?
Means when we are trying to solve such questions, whether any real number also we should
Any
consider. That is my question.
Any real
Okay,
number.
as a matrix, any real number should also be considered for checking the condition.
Okay, so you are saying
Whether
that
n can be equal to
yes. So you are saying that n. So your n is 1, and then n cross n is your just one entry, and in that case trace could be negative for n.
yeah.
So if I take minus a, then trace will be just minus a, and which is less than 0. That was your.
Whether this condition is valid.
Yes,
If
yes,
it
yes,
satisfies.
definitely. Yeah, I mean, this is for any given n, so I don't think this would create any problem. Yeah, this is also fine. Yeah.
Okay.
Yeah, because I can just stop it here, like diagonal of single -1, and then still it becomes -2, and it is less than 0. Yes. As far as you find the counter example, and there is no condition on n given, you are good to go. Yeah. Any doubts?
In this
Yes, sir.
problem, linearity also fails.
Linearity would also fail.
Yes, suppose I take A as 0 matrix, B non-zero matrix, but inner product non-zero.
Yes, yes. Inner product of 0 with anything must be 0. Yeah, that condition. Yes. You can take 0 outside and 0 into something. Yeah. That would also be, that will also create problem here. Yes. Yes. So now any doubts? I think it is clear now, right? Okay. So let us move to now second question. Just a second. Let V be an inner product space and not V. Let in R2 consider a inner product space inner product given by this x1 comma x2, this y1 comma y2, and this is defined to be x1 y1 plus square root 3 x1 y2 plus square root 3 x2 y1 plus 3 x2 y2. Okay, and then find the length of the vector 1 comma root 3 in the norm with respect to this inner product. So we have to find norm of this vector 1 comma root 3. And what this is? So they are talking about this they have already said that this is inner product. So we don't have to check that this is inner product or not. Okay, it is already given. So this is inner product and we have to find length of this vector. So length of this vector means the norm of this vector with respect to this given inner product. So every inner product induces a norm. Okay, and this will be this 1 comma root 3 comma 1 comma root 3. Inner product, square root of inner product. Okay. So and given inner product is what? So instead of writing square root every time, let me take square on both sides. And then it will be what? 1 into 1 from the definition x1 y1. So 1 plus square root 3. x1 is 1, y2 is root 3 plus root 3 into x2 is root 3, 1 plus x2 3 root 3 root 3. So this is 1 plus 3 into root 3 root 3 3 root 3 plus this is 9. So this becomes 16. So then this becomes 1 comma root 3 is equal to norm of this will be 4. Any doubts here? Just basic calculations.
Ma'am, can you please explain? I could not understand.
So norm
Calculation
of
came.
norm of V is square root of inner product of this. Okay, because we anyway have V comma V, or it's always greater than equal to 0. I mean positive if V non-zero and 0 if V is 0. Okay. So this is there. So this is definition. And this thing is called length of vector V. Okay. With respect to this inner product. So this is what? This is square root of this 1 comma root 3, 1 comma root 3. So our V is this 1 comma root 3 in this case. So I'm taking inner product of this element. So this is 1 root 3 and this is another root 3. I mean, so like this. So element the inner product with itself. Then what is inner product? It is given x1 comma x2 y1 comma y2 is this x1 y1 plus square root 3 x1 y2 and so on. So just I did that. I took just square on both sides so that this becomes, so instead of writing square root everywhere, I'm just taking square and then this becomes 1 into 1 because x1 y1 plus root 3 into x1 which is 1, y2 is root 3 here, root 3 into x2 is root 3 and y1 is 1 here, and last one is this root 3 into root 3 because both x2 and y2 are root 3. So 3 into root 3. So just substituting x1, y2 in this equation. And then I'm just multiplying the 1 root 3, root 3, 3, root 3 into root 3, 3, this root 3 into root 3, 3, 3 into 3, 9, and adding this becomes 16. And now I just need to find the norm. So I'm taking square root, and this is 4. And note this, you can't take this to be plus minus 4 because norm is defined to be non-negative number. So it has to be 4. Is it okay?
Here, what is x1, x2, and y1, y2?
This is x1, this is x2, this is y1, this is y2, because that's how it is defined. So this is this. Okay, so if I am to highlight, consider see this and this. Okay, so this is how the inner product is defined. So now this is the definition. It's just substituted it as it is. Is it okay now?
Yes, yes.
So it is now any doubts here? Please let me know. Otherwise, I will move to next question. If you still have doubts, please let me know. So let V be an inner product space. And let S is equal to V1 to Vn be a subset of V. Then we have to check which of the following. So given condition is that V is inner product space and S is set containing these elements V1 to Vn of V, and we have to check which of the following statements are true. Okay. So first statement is, if S is an orthogonal set of vectors. So if S is orthogonal set of vectors, then S is linearly, then S can be linearly dependent. So they are asking that if S is orthogonal set, then is there any possibility then S could be a linearly independent set? So what is your guess? Is it possible for orthogonal set to be linearly dependent set?
No.
No, right? So if you are saying no, then we kind of need to prove that this can never happen. So give me any orthogonal set. I need to show that it can never be linearly dependent set. Right? Because they are saying that S can be linearly dependent, which is not true. So
we can take standard basis.
Yeah. So but P is any given.
Yeah.
Okay. So since given that S is orthogonal set, and we have to show that S is linearly dependent. So what linearly dependence means? So that suppose S is linearly dependent, then what does this imply? That basic definition of linear independence. This implies that this A1, V1, A2, V2 plus AN, Vn is 0, and at least one of AIs is non-zero, right? This is true, right? This is the definition of linear dependence, that we get non-zero linear combination which gives us 0, right? So this implies, so suppose without loss of generality, let some AI to be non-zero, then I can very well write this Vi to be this new element. So I will now what do? I will divide everything by AI, then it becomes A1 dash V1, A2 dash V2, so on up to A3 dash vi minus 1 plus, sorry, ai minus 1 dash, ai plus 1 dash, vi plus 1, and so on up to some this an dash vn, where ai dash or aj dash is what? aj comma divided by ai. This is okay? Minus, or let me write this minus. Is it okay? Or if you don't like this, we can just write this to be b1, b2, bj. Just I'm manipulating the coefficients. Okay. Then they have given that this set is orthogonal set, right? So what I can do is, if I take vi comma vi, then it has to be non-zero, right? Since vi belongs to S and orthogonal set. But what is vi comma vi? If I substitute this vi here as it is, this b1 v1 so on up to bi minus 1 vi minus 1 plus bi plus 1 vi plus 1 plus bna vn, there's no space, comma v1, sorry, vi. Then what this is b1 into v1 comma vi plus b so on up to bi minus 1. So I'm taking the scalar outside and splitting this at the same time, and so on. Let me write this as well. bi plus 1 into vi plus 1 comma vi plus bn vn comma vi. But none of them is equal to I, and since S is orthogonal set, vi comma vj is 0 for I not equal to j, right? Because since S is orthogonal. So then this becomes b1 into 0, so on up to bn into 0, which is 0. So this is contradiction to orthogonality of S, because orthogonal set, inner product of element with itself has to be non-zero. Is it okay? Any doubts here? So that's why it can't be linearly independent. Sorry, linearly dependent. Please let me know if there are any doubts or how things are going or anything is unclear. So this implies if S is orthogonal set, then it has to be linearly independent set.
So this follows from the proposition also, right? Which was proved in the
Okay.
lectures.
Okay. Okay. If that is the case, then that's good. But I just wanted to
I'm just
clear.
checking that the proposition was the same, right?
Could you please let me know what is the proposition in the from the lecture?
So V is an inner product space over F,
Mm-hmm.
and V1 to Vn are vectors in V, which are orthogonal to W in V. So then any linear combination of V1 to Vn is orthogonal to W.
Yes, yes. I mean, so in that case, we do not need to have this entire calculation. We can do that from here itself.
Yeah.
Yeah. Then from that proposition, from here itself, the proposition follows, and we can get that because vi has inner product 0 with all p1 to vi minus 1, vi plus 1 to vn, and this vi now has become the linear combination of them, and then vi into vi has to be 0 from the proposition mentioned by the sir. So yeah, so we do not need to do this calculation in that case. But those who do not know that proposition, is this clear? Or if, I mean, yes, definitely, sir. As you said, from the proposition, it clearly follows. We do not need to follow all this calculation. The moment we get this, that this is non-zero linear combination, one of them is non-zero, and we can very well write them as a linear combination of others, one of them as a linear combination of others. And from your proposition, it follows. Yeah. So any doubts here? Okay, I'll move to next question. If S is an orthogonal set of vector then dimension of V is greater than equal to n. And any guesses for this one? That if S is an orthogonal set, so S, as we are already given, is V1 to Vn, so S has cardinality n. So what they're saying is that if we have orthogonal set of cardinality n, then dimension of the vector space V is greater than equal to that n.
If S forms the basis, then it would be n. But if S does not form the basis, then we need to check whether
Yes,
there's any
yes,
basis with.
yes. So what he's saying that, but yeah. So it is we already from what we did in first example for this, from one, S is orthogonal set, then S is linearly independent, right? So therefore the dimension of V is the cardinality of maximal linearly independent set. Okay, so cardinality of basis is the cardinality of maximal linearly independent set. So that's why this becomes so that's why this becomes the cardinality of maximal linearly independent set. Dimension of therefore dimension of V is greater than equal to n, since n is linearly independent set. Is there any problem? So dimension has the maximal cardinality of linearly independent set. So any set having cardinality greater than dimension of vector space is always linearly dependent. So here we are already given that n is a linearly independent set. So if, as I said, if it's forming the basis, then it is equal to the dimension, because then that linearly independent set is becoming the basis of that vector space. So it is equal to the dimension. But if it is just a linearly independent set, so there could be some other elements which are forming the basis. We need to add those elements to the basis. So that's why this cardinality of independent set need not be equal to the dimension. That's why in that case, this n will be less than equal to dimension of V. Is it clear?
And that greater, how it will come? Equal to n is understood, but under what condition
So
the
for
dimension?
example, if for example, let us take R3. Okay. This is orthogonal set. Is this orthogonal set? Hello?
Yeah.
Yes, this is orthogonal set. So, and cardinality of this is my orthogonal set in S. But what is dimension of R3? It is 3. Dimension of R3 is 3, which is strictly greater than this n here, which is cardinality of S.
Okay.
Is it okay?
Yes.
Yeah. Let me write 2 here. Okay, so this asserts it that if it is a basis, then it will be equal to, but if it is not, we need to add few more elements for it to become a basis, and then the dimension will be greater than this n. Okay, so that's what he was referring to actually. So is this clear now? Any doubts, please let me know. Okay. So this third one, the last, not the last one, but yeah, third one, that norm of v1 plus v2 plus so on up to vn square is equal to norm of v1 square plus norm of vn square if S is orthogonal set. So they are saying that if, so this is true. So they are saying that if S is orthogonal set, then this norms becomes equal. So this becomes equal.
Yeah, that's true based on the generalized Pythagoras theorem.
Yes, yes. So how this follows is actually that let me just prove it. Okay, so what is this? Norm square is square root, not square root. It is already square. So this is v1 plus v2 plus vn comma v1 plus v2 so on up to vn. And since S is given, inner product space, okay, base field is not given, so let it be. But then in that case, since coefficients are anyway 1, 1, 1 here for v1, so this becomes v1 comma v1 plus v1 comma v2 plus so on up to v1 comma vn. And now for the second, v2 comma v1 plus v2 comma v2 plus v2 comma vn and plus v3 comma v1 v, or let me just write dot 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 plus vn comma v1 v2 vn comma v2 plus vn comma vn. And since this is orthogonal set, this vi comma vj is 0 for is equal to 0 for I not equal to j, and for rest this is just it stays, right? So this becomes 0, this becomes 0, this becomes 0, this becomes 0, because we are in orthogonal set, and this becomes 0, this becomes 0. So only thing remains is this vi comma vi kind of things, plus v2 comma v2 plus vn comma vn. And then what is this? This is just, if I just write everything, then this becomes v1 plus vn square. And by definition, this is norm of v1 square plus norm of vn square. Is it okay? Hello? I'm still audible, right? Hello?
Yes, sir. You're audible.
But is this clear?
Yes.
Okay. So if there are any doubts, please let me know. Okay, so this is happening because the second coordinates here are just 1, 1, 1, 1. So we don't need to check about the conjugate symmetry because we are dealing with the coefficient is equal to 1. Okay, so that's why. So let me move to now next question. The fourth one. And this is this v1 plus v2 square is equal to, oops, not plus, this v1 minus v2 square is equal to 2 norm of v1 square plus norm of v2 square. And what is your guess? If holds only if, so they are asking that this holds only if S is orthogonal set. So what is your guess then? They are saying that this happens only if S is orthogonal set. So for this to happen, they are saying that S has to be a orthogonal set. So
Yeah, that
what
is
is your
true because v1 minus v2 norm square is again v1 square, norm of v1 square plus norm of v2 square.
sorry? Uh, okay. So they are
So
saying that
v1
this
plus
happens.
v2 norm square is v1 square plus v2 square from the Pythagoras theorem. And v1 minus v2 norm square, since
Okay.
minus
Hmm.
v1 v2 and v2 v1 would be 0. In that case, you'll again land with the same
Become,
thing. Yeah.
yes. Yes, that is correct. So that happens when S is orthogonal. But they
Ortho.
are saying that this happens only if S is orthogonal. So they are saying that if I have
Mhm.
two elements v1 and v2 which does not form orthogonal set, they are saying that in that case this element, this identity does not hold. So is that true?
So it
They are
depends on
saying
how
that
we take v1 and v2.
exactly. So can we give a counter example that v1 v2 are not orthogonal, but this inner product is definitely, I mean, this identity holds. I mean, what you said for the set of orthogonal is completely true. But does that, I mean, does this identity hold only for orthogonal set? That's the question.
Mm,
So
Suppose take v1 equal to v2.
so if we take v1 equal to v2, then v1 equal to v2, then what will happen? This is norm of 2 v1 square is equal to 2 norm of v1 square plus norm of v2 square, which is 2 into 2 norm v1 square, oops, which is 4 norm v1 square. And here when we take norm square, here 4 comes out. Is it or it doesn't? It has to be, right? This is v1 square, but is it? Or if that is not, let us take v1 to be anything and let v1 belongs to v and v2 to be 0. Then in that case, norm of v1 plus v2 square plus norm of v1 minus 0 square will be what? 2 norm of v1 square, right? Because this is 0, this is 0, so this is just, and 2 norm of v1 square plus norm of 0 square is just 2 norm of v1 square. So this is equal. Okay. So yeah, I mean, we can take any examples like v1, v2 equal and everything. So that is not a problem. Is it okay? This is first counter example. This is second counter example. Where this happens, but v1 comma v1 is not orthogonal set. But v1 comma 0 is not orthogonal set. Any doubts? So the moral is that this identity is, for this identity to hold, S need not be an orthogonal set. Okay, so let us do this. The fifth one, which says that norm of v1 plus v2 square plus norm of v1 minus v2 square is equal to 2 norm of v1 square plus norm of v2 square. Holds. Now they are saying for any v1 comma v2, for any two vectors v1 comma v2 in V. So let us check whether this holds for any. So let us start with LHS. So it is norm of v1 plus v2 square plus norm of v1 minus v2 square. So what is this? This is v1 plus v2 comma v1 plus v2, right? By the definition. Just writing the definition. Okay, and there are no complex numbers here as the coefficient. We can just simply split them. And we get v1 comma v1 plus v1 comma v2, or let me do this, v1 comma v1 plus v2 all. So this is for the first one, and this is v1 comma v1 plus, not plus, the minus v2 comma v1 plus v1 comma, not minus v2, minus minus becomes plus v2 comma v2. So then these two things get cancelled, this with this and this with this, and we are left with, this is norm, so 2 norm v1 square plus, did I do anything? Yeah, correct. Norm of v2 square. Here also we get 2 norm of v2. So this here and this here. Is it okay? So this holds for any given two vectors. So let v1 comma v2 in V. Any doubts? So you can use this identity for any, my 2 doesn't look like, holds for any vectors v1 and v2, they need not be orthogonal. Okay, so let us move to next question. Please, if there are any doubts, please let me know. So let V be a vector space over R, and W be an inner product space over R with inner product and assume that T from V to W is linear map. Okay, so they are saying that T is a linear transformation. So for x comma y in V, we define this new map x comma y dash to be inner product of tx comma ty. So V is a vector space and W is an inner product space. So W has inner product with it. And they are saying that we have to assume that T is a linear transformation from V to W. So W has inner product, and now they are defining this new map x comma y dash which is equal to inner product of Tx comma Ty, which is this inner product in W, which is already given to us. Okay, so now we have to check the box, check whether the following statements are true or not. Okay, so first one is that for every linear transformation T, we have this new map is an inner product over V. And what is your guess? So they are saying that T need not have any condition. Given any T, this map defined here, this x comma y dash is it forms inner product on V. Any guesses here that whether this will always form inner product on V for any given linear transformation T from V to W? So all the three conditions of inner product space will be satisfied for any given T. That's what they are asking. Any guesses?
Should be true, right? Because linearity is satisfied. Symmetry would also be satisfied.
Yes.
And positivity would also be satisfied.
So positivity.
I think it should be satisfied, but
Okay, so positivity will satisfy if, so what is positivity? It is like for any x comma x. So x comma x for x non-zero. If I have x comma x dash, then I need to have this to be greater than 0. So what does this imply? That this tx comma tx must be greater than 0, right? By the definition. But how can we guarantee that just because x was my not, I mean this to hold that tx must be non-zero, right?
but it is in R, so it can be negative also.
Yes, because it is a map. We can have a map such that non-zero element is mapped to 0 element. Then in that case, this x comma x dash will be equal to 0 by the definition. Okay, so that will not hold. So simply take T from V to W. Let V be a non-zero vector space and T is from V to W. So W be any space which has inner product. Then we can take this map, right? Everything is going to 0. So in that case, for any non-zero x, since V is non-zero, we can have this x comma x dash is what? Tx comma t dash. So tx comma tx, and which is always 0 comma 0, which is equal to 0. Okay, so this is not true for any given linear transformation. Zero transformation is very well, it is a linear transformation which does not have this property. Is it okay?
Yeah.
Yeah. So this does not hold for any given, I mean linearity satisfies, but positivity would create problem because non-zero element can give us 0 as an inner product. Okay, so this is not inner, I mean this statement is not true. So second one is that if T is surjective, then this again is an inner product on V. So they are saying that now they have put condition on T, and they are saying that if T is surjective, then this becomes inner product space. And what is the guess? T is surjective, can we always say that this forms an inner product?
Surjectivity only guarantees you that there is an x corresponding to a y.
Uh-uh. But it
Uh,
does not guarantee whether that y will be 0 or not.
yeah.
Yeah. So it would not satisfy as suggested by sir. So can we have an explicit example where this is not holding? So if we take W to be 0 space, that is quite trivial example. So we can start with V non-zero, W is 0. So 0, 0, everything is satisfied and not a problem. But can we have a non-zero vector space such that this T is surjective, but this map X, I mean, the map is not inner product on that space with respect to that map? So we have to have surjective such that at least one element is such that it goes to 0. With non-zero element goes to 0. So let us create such map. So let T be from R3 to R2, and we can have this x comma y comma z going to x comma y. So this is surjective map. This is clearly a surjective map. Then T is surjective map for z non-zero. This element 0 comma 0 comma z comma 0 comma 0 comma z will be what? T of x is x comma y. So it is 0 comma 0 comma 0 comma 0. This becomes 0. Okay, so therefore this T, this does not hold positivity for this T. Okay, so that's why this statement is not true. That T being surjective does not guarantee that this map x comma y dash forms inner product on V. Okay, now third condition, that if T is injective, then this is an inner product space. Oh, not, it is an inner product on V. And now what is your guess? Does injectivity guarantee that non-zero x goes to non-zero x?
Injectivity would be one-to-one mapping, right?
Yes, yes.
So for a zero case, it would only go to 0.
Yes.
So we'll consider all those cases where it's not a 0 map.
Mm-hmm.
Then we can say it's an inductor. But
Yes.
that's a
Okay. So let us start proving all the conditions. So initially our guess is that it would hold because x goes to non-zero, x goes to 0 is okay, but non-zero x goes to non-zero element when T is injective, right? So we have proved this long back in our tutorial. So let us start with this. And now let us take this x comma y, x plus y comma z. Then how it will be? Dash is T of x plus y comma T of z, right? And this is T of x plus T of y because T is linear map, and from the linearity of inner product in W, we are getting this. Okay, so understand that why these steps are following and what is the reason behind them. Or if I take this Cx comma Z dash, then this is what T of Cx comma Tz. And then this is what Ctx, because T is a linear transformation. And because of linearity in the first coordinate for the inner product in W, we have this. Okay, so the linearity is satisfied in the first coordinate. Now we are moving to second condition, which was about conjugate symmetry. So x comma y dash will be what? It is Tx comma Ty, right? From the definition. But because of the inner product on W, we have this. And now this becomes what? Y comma x conjugate. This is dash and this is conjugate. So conjugate symmetry is there because note that this, whatever is under that conjugate sign is equal to this element. Okay. And now the last one. Now the positivity part. Okay, so since T is injective, kernel of T is what? Just zero element. Okay, so if anything is going to zero, it is only a zero element which is going to zero. So that is what? That if x is non-zero, then T of x is non-zero. Okay, so therefore, for x non-zero, x comma x dash will be what? Tx comma Tx. And this is greater than 0 since Tx is non-zero and is inner product on W. So therefore positivity holds. Is there any doubt here? So that's why this forms inner product. So injectivity guarantees us that T being injective guarantees that this forms a inner product on V. Any doubts here?
Ma'am,
Yes.
can you go first condition, ma'am?
Yes. So T is injective. Injectivity means kernel is zero. Only element which is going.
This is I understand, ma'am.
Mhm.
Go to first condition.
This first condition.
This first condition before doing that, because
Here?
network issue.
Okay, this one here.
No. Before slide.
This
Before slide.
previous slide. Okay, this one.
First one.
The very first one. Okay, this. That every linear transformation T.
Here zero linear transformation not working, ma'am.
Why, sir?
So zero linear transformation gives zero.
Yes.
In that case, positivity not working.
Yes. That's why it is not inner product, because positivity is not working.
Okay.
Mm-hmm.
Okay, ma'am. My side network problems. I can't.
Okay, no problem. But is it clear now to you?
Oh yeah, I clear.
Yeah, okay. And this one, if T is injective, please let me know if there are any doubts here. Okay, so injectivity guarantees that this T will, this x comma y dash is actually forming inner product on V with respect to this injective linear transformation T. Any doubts here? Please let me know. The linearity is not a problem and symmetry is also not a problem. The main problem was the positivity here, as also we observed earlier. So the guarantee that x non-zero gives us that Tx non-zero assures us the positivity is true in this case. Okay, so now the last not of this question, or let me do this. 1, 2, 3. Or this fourth is that this again is an inner product if and only if T is bijective. So we proved that if T is injective, then inner product happens. But they are saying that if this dash gives inner product if and only if T is bijective. So what is your guess here? If and only if means that if this dash is forming inner product, then the map has to be bijective.
No, right? Because we proved it for injectivity and it did not pass surjectivity. So
Yeah, exactly. So can we just give a counter example where the map is not bijective but it is injective? Then that would hold, right? Because then in that case it will violate the only part. Okay, so let us do this map. So let us go from R2 to R3. So let T be from R2 to R3. Then and such that x comma y is going to nobody's here. X comma y comma 0. Okay, so then in that case this map is injective, but this is not a bijective map. This map is injective. So by previous, so since T is injective, therefore by previous result, this is inner product on V, but T is not bijective. Therefore, only if part does not hold, and that's why this statement is false. Okay, is there any doubt here? This is injective map, which is giving us inner product by previous result. So surjectivity is not needed for this to be. So bijectivity is not the only thing which will give us inner product. Only injectivity, and we are sure that this dash will form a inner product space. Is it okay? Hello?
Okay.
yes, fine.
Okay. Sorry for the interruption. Okay, so I hope this is clear. If there are, you can have plenty of such maps which are not surjective but injective, and the map will give you the inner product with respect to this x comma y going to tx comma v ty. But the map was not bijective and so on.
I think this searching of these maps is a bit of a challenge.
Yeah, but one thing I can tell you is that injectivity, we need injectivity, right? So if we can take a map from n-dimensional space to m-dimensional space where n is strictly less than m, then since it is not bijective, we know that something is bijective if and only if, so linear map is bijective if and only if dimension of v is equal to dimension of w in finite dimensional case.
Yeah.
Yes, so we can do something of that sort, because if you take dimension of v to be n, which is strictly less than dimension of W to be M, then by the rank nullity theorem or dimension theorem, the dimension of kernel will always be, sorry, the image will be injective, the full rank. Or sorry, the nullity will be 0 and so on. I mean, I hope you understand what I'm trying to say. The nullity will be 0, but dimension of what I'm saying, V is equal to dimension of V is equal to rank plus, yeah. So what I'm saying is that image will have same rank as dimension of V, but the nullity will be 0 in that case. So map becomes injective but not surjective, because dimension of W is something which will be strictly greater than rank of T. And this will give us a non-surjective map. I mean, I hope I'm not confusing you. I'm just saying that try to choose dimensions and use the dimensions to arrive at the counter examples and so on. That's it. I mean, see, this is just kind of image or taking injection inside R3 with last term is equal to 0. So this is injective. Okay, but not surjective, because one more dimension and it is going nowhere. Okay, any map you define on this from R2 to R3. Okay, the dimension of range will be 2 or less than 2. That is for sure. That assures from the rank nullity theorem, because it is what dimension of V is equal to rank of T plus nullity, right? So nullity could be anything. Nullity is also now null space is inside null space is inside V. So dimension, so this nullity is less than equal to dimension of V, because subspace, we know W is subspace of V, then dimension of W is less than dimension of V. So this V will be either 0, 1 or 2, right? And here is also 0, 1 and 2. And we know dimensions, this rank is also dimension of image, this T of V or image set, right? So here it is 0, 1, 2. And since everything is positive here, it has to be 0, 1, 2. Okay, so rank is maximum 0, 1, 2. But our W had dimension 3. So this is non-surjective map. That's what I'm trying to say. That take any linear transformation from R2 to R3. Rank will either be 0, 1 or 2. Okay, the 0 map will have rank 0. For example, x comma y going to x comma 0 comma 0, then rank will be 1. The maximum rank will be 2. It will never be 3, because in that case, if rank is 3, that is, it is a surjective map, then this is 3 plus something non-negative is equal to 2. And this is absurd. This will never hold. Okay. So that's what I'm trying to say when I said that try to do things with dimension.
Okay.
Yeah. Sorry. Yeah. So we'll move to next question. I mean, I hope this was okay. If not, then please let me know. But if okay, then we'll move to next question. This question 5, that consider the vector space C 0, 2 pi, yeah, comma R of continuous real valued functions defined on the interval 0 to pi, okay, and with inner product f comma g is equal to integration, so it is 1 by pi first, integration 0 to 2 pi fx gx dx for f comma g in this space C0 2 pi r. So then whether the following statements are true. Then check whether true or false. Okay, so first one is that let f comma g in C 0 comma 2 pi to r be such that this norm f is 1, norm f plus g is 1, and norm of f minus g is 3, then not true of it. Then find the value of norm g square is. And what shall we do here? We proved something just now before coming to this, where it went. Yeah, this identity. This is true for any vectors, right? And here also they have talked about norm of f, norm of g, norm of f plus g, and norm of f minus g. Okay, so we will use that identity, and we know that norm of f plus g, right? It was f plus g, f minus g is equal to 2f square plus norm g square, right? It was this identity. So this imply what? That norm of f plus g is given to be 1. So this is 1 square. Norm of f minus g is 3 square. 2 into norm is 1 square plus norm g square, which is asked. So this is what? 1 plus 9 by 2 is equal to 1 plus norm g square, which is 5 minus 1 is equal to norm g square. So this is 4 is equal to norm g square, and this will imply that norm of g is 2. Any doubts here? Just simple calculation from the given identity. And it is given that this is inner product space. Okay, so already given that inner product space, that's why we could use this. Is it okay? Oh, or they have just asked about
Okay.
norm of g square and it is 4. They did not ask about norm of g. So yeah, it's okay. Any doubts here? Just applying this identity, which we already proved in preview, just before a few minutes. Is it okay?
Just a quick question. So
Yes, sir.
if I try to solve it using the first principles, that is not going to this equality, then I need to solve the inner product first, right? So for
Yes.
norm of f equals to 1, I'll say that that would be square root of 1 is equal to
Yes,
1 pi.
yes. So norm of g square, you are saying it is just g comma g is this 1 by pi 0 to 2 pi. That's what you are saying, right?
Yeah.
And what is g?
Gx to gx.
But yeah, that is true. But here explicitly the g is not given to us. Even f is not given. Nothing is given. Just the norms of these elements: f plus g, f minus g, and f.
But I have the integral value, right? Which is equal to say something. Say for f, if I start with f, the integral value is 1.
So what you can do is, in that case, okay. But still, what will you integrate? That's my question. You don't know what f is or what g is. Forget about it. What g's, we don't know. So what will we integrate? Because there will be like infinitely many functions which would satisfy this property. So which will you integrate? I mean, but from this property or this this equality or this identity, if we have any f and g which satisfy these three things, that norm f is 1, norm f plus g is 1, and norm f minus g is 3, then that g here mentioned has to have norm square is equal to 4. Okay, so I mean, what you said, if g was given and if they had asked me the norm of g, then I would happily go ahead with doing integration and so on. But here we don't know what g is. So what will we integrate? Okay, so that's why we needed to use this identity. And I would suggest that please all the identities which are given in the lectures, which are there even in the assignments. Okay, there are, I think the assignments, if you had seen for this week's, there are many identities given. If possible, try to get hold of those identities. Try to kind of not completely memorize it, but kind of try to recall it if needed, because those will come handy in such situations. Because if we don't know this identity, what will you integrate and how will you go ahead with anything?
Okay.
Okay, I mean, yeah. Yeah. So next is second one is that let fx. So now fx is given, that fx is cos x and gx is sin x. It is given now. Okay, now they are asking us to find value of this inner product f and g. So now we have to do this integration, that f comma g. Now there is no identity can play role in here, because we already have fx given, gx given, and they are asking us to find this inner product f comma g. So it will be 1 by pi 0 to 2 pi cos x sin x dx, and now this is 1 by pi. So if you know, this is 2 sin x cos x is sin 2x. So this will be sin 2x by 2 dx, and this becomes 1 by 2 pi. This is 2 pi sin, sorry, minus cos 2x by 2, 0 to 2 pi. And what this is minus 1 by 4 pi. This is 1 minus 1, and this becomes 0. Right? Cos 0 is 1, cos 4 pi is also 0. Sorry, cos 4 pi is also 1. So 1 minus 1 becomes 0. This f and g. The inner product of this is 0. Okay. Any doubts here? Just normal integration. I did nothing else.
So sorry, I think it should be minus cos 2x that divided by 2 has already been taken out, right?
But this differentiation 2 should be there, na? Cos 2x.
Yeah. For sin 2x, you would have
Yes.
minus. Okay.
Okay, is it okay now? Okay, so let now the third one. Let gx is equal to sin x. Now the value of norm g. Now see, now the gx is given and now they are asking the norm of g. So no identity I required. I'll just go ahead and solve the norm of g. Okay, so norm of g square is what? Inner product of g comma g. So this is what? Integration 1 by, so from the inner product, the definition, it is sin x into sin x dx, and which is 1 by 2 pi integration 0 to 2 2 pi sine square x, and this will be 1 by 2 pi. No, 2 pi, only pi. Only pi, 0 to 2 pi. So sine square is 1 minus cos 2x by 2 dx, and this is 1 by pi integration 0 to 2 pi 1 by 2 dx minus integration 0 to 2 pi cos 2x by 2 dx. And this here will be 1 by pi into, this will be 1 by pi 2 into 2 pi minus 0 minus 1 by pi into, here it will be cos 2x will be sine 2x by 2 from 0 to 2 pi, and here it is 1, and this sine 0 is 0, sine 2 pi is also 0. So this is 0 minus 0, so 1 by 2 pi 0 minus 0 or 4 pi, let me be precise. And this will be just 1 minus 0, so 1. Therefore, this norm of g square is 1. So therefore, this norm of g is 1. Okay. Now is it clear? Now the function was given. So when I have to calculate the norm of this g, it will be just calculating everything, doing integration and so on. Is it okay?
Yeah.
Okay. And now this is last question. So let A, B, C, and D in R, and check whether the following statements are true or not. Okay. The first one is A square plus B square, C square plus D square is less than equal to AC plus BD square. So this is true for any ABCDs. That's what they are saying. So what is your guess? Will this always be true? That for any given ABCD in R, this identity is always true. That's what they are asking, whether this identity is true or not. Choose ABCDs which will give us contradiction. So that is the hint.
So I can take D equals to minus C.
D is equal to minus C. In that case, what will happen?
And I can take A equals to B.
Okay, A is equal to B. Then this will become 2A square, right?
Yeah.
This becomes still 2C square, right?
Yeah.
And but this is what? This becomes 0.
Yeah. 0.
A minus or minus A plus A square, so which is 0. This becomes 4A square C square less than equal to 0, which does not hold when C is, oops, A, C non-zero. Let A non-zero, C non-zero, and let me write this. And D is equal to minus C, B is equal to A. Now is it okay? So if my D, A and C are non-zero, then this is something strictly, this is positive. Okay, but this, some positive is strictly greater than zero, which is not true. Okay. So now second one. That A square plus C square, any doubts? Someone? A square plus B square, C square plus D square is greater than equal to AC plus BD whole square. Is this always true?
This should be true.
Yes, this is true. So how to go about it? So note that this statement implies what? That A square plus B square into C square plus D square minus AC plus BD whole square is greater than equal to 0, right? These two are equivalent. Just taking the left hand side, sorry, right hand side on the left hand side. Okay. So these imply what? If I simplify this left hand side, then it is A square plus B square, or let me just, so let me write here LHS is equal to A square C square plus A square D square plus B square C square plus B square D square minus A square C square plus 2ACBD plus B square D square. And this is what? AC and this BD gets cancelled, and we are left with A square D square minus 2ACBD plus B square C square, right? And if, just to make this clear, I can make this as AD BC plus B square C square. So then this becomes AD plus BC, AD minus BC whole square. And which is anyway greater than 0, which is RHS as we needed. Therefore, if I call this star, then this star is true. Okay, so this statement is true, or therefore star holds. So is it clear? Just simplifying the given properties, not properties, I mean given terms. Then doubts here? Okay, so I assume there are no doubts. And this is, next two questions are interesting. So let us do this. If A plus B plus C plus D is equal to 1, then 4A square plus B square plus C square plus D square is less than equal to 1. So is this true, false? If false, counterexample. If true, how to prove this? They have given that A plus B plus C plus D is equal to 1, and then this is the statement. So this will be false because we can take A to be 1 and let take B, C and D everything to be 0. Then A plus B plus C plus D is equal to 1, right? But this 4 into A square, B square, C square will be what? 1 square plus 0 square plus 0 square plus 0 square, which is 4, which is not less than equal to 1. Okay, so this is not true. Okay, just start with ABCD is equal to 1 and this will not hold. Is it clear? I mean, this example, I mean, we can have many such, but this was the simplest one, which I found. So we are over time, but this one will solve. So this is last one of the same kind. So if now they are saying that if A plus B plus C plus D is equal to 1, then 4A square plus B square plus C square plus D square is greater than equal to 1. And now what is the guess? Prove this, or do you have any counter examples here?
So I can always say that the equal inequality can be stated as a square plus b square plus c square plus d square is greater than equal to 1 by 4.
Yes.
And then here I can say is a equals to b equals to c equals to d. Then that would be 4a equals to 1, for example. Then a is equal to 1 by 4.
Yeah, that is true.
At least I'm proving that it is equal to 1 by 4 is the minimum I can get.
No, but this is just ABCD in R, which is giving you 1, right? So I can very well have this 5 plus minus 4 plus 0 plus 0 is equal to 1.
Mm.
In that case, I mean, we can't say that ABCD has to be 1 by 4. For any given ABCDs such that A plus B plus C plus D is equal to 1, we need to show that this is true. This is, I mean, these are general statements for any given ABCDs in R. So then in that case, what is your guess? At least guess. I mean, not the proof or anything. I mean, what is your guess that this statement is true or false or what it is? Or it is inconclusive. For some cases, is it positive? So for some cases, is it negative? So, but if that is the case, then this is false, right? If for some it is not true. So, any guesses?
This would be true because if I even consider negative values, then they would turn positive here, and I would have a value which will be greater than 4 because greater than 1 because we are multiplying it by 4.
Yes, I mean, it looks like that it has to be like the statement should be true, right? So let us try to prove this then. So we have this in the lecture that something called as Cauchy
Mm.
force inequality. Okay, and which states that if let V be an inner product space over F for V comma W in V, we have norm of V comma W less than equal to norm V into norm W. Okay, so so this is inequality which we have. So we have to now smartly choose a inner product over R or R4 because we have these 4 elements such that this we should arrive at this. Any guesses for inner product? Okay, so let me just start with it. So let P be R4. And we know that the basic inner product A1, B1, C1, D1, comma A2, B2, C2, D2 is equal to A1, A2 plus B1, B2 plus C1, C2. This is like usual inner product on Rn, which I am defining. And this is inner product, okay? There is any doubt here that this is inner product? No, right? I assume that there is no doubt for now in this. So this is inner product. So V comma this forms an inner product space over R. Okay, since this ABCDs and everything is over R, we can assume this to be over R. Then note that then Cauchy squares will be what? So if I am to write this in the fashion of Cauchy squares, then it would be like this, right? A2, B2, C2, D2, yeah, is equal to norm. So norm is what? Norm is square root of A1 square, B1 square, C1 square plus D1 square into square root of A2 square, B2 square, C2 square plus D2 square. Is it okay? This is just norms I'm writing. So this is something which is on the lesser side and this is on the bigger side. So we have to choose now ABCDs. So if I take the elements to be 1, 1, 1, 1 and the element A, B, C, D, then inner product of this will be what? Just A plus B plus C plus D, right? If I take this to be V1, this to be V2, then let me write this, that, or let me take W and V comma W, inner product will be just 1 A plus B plus C plus D, right? And this is anyway given to be 1. And what is norm of V into norm of W? This is square root 1 square plus 1 square plus 1 square plus 1 square. And this is square root A square plus B square plus C square plus D square. And this is what? Square root 4 into square root A square plus B square plus C square plus D square. So by Cauchy squares inequality, we get what? This 1 is less than equal to the square root 4 into square root of A square, B square, C square plus D square. And I can happily now take squares on both sides and this will still hold. Okay, sorry, this 4 into. Note that here this 1 is important. Okay, so this, I mean, A greater than B does not imply that A square greater than B, okay, B square. This is not always true. You can work on this. This does not always hold. Since here 1, I mean, something on the RHS was greater than 1, that's why this could hold. I mean, the square greater than, I mean, the square followed the inequality of initial inequality. Is it okay?
Yes.
Okay. So this proved this inequality. Okay. And this V is equal to R4 was not any space. I mean, of any significance. This is true for any Rn. We can prove this. And here, instead of square root 4, we will get square root of n. And here, a1 square, a2 square up to an square. And this will give us 1 less than equal to n into a1 square, a2 square, and an square. Okay, so this had no significance of R4 in general. Okay, this could be proved for, this can be proved for any V is equal to Rn. Is it okay? I mean, yeah, this is not very natural or intuitive, because to start with, I mean, to think from just these numbers, to think that we can connect this to the inner product is difficult in itself. But yeah, it is like this. So is it okay? I mean, there are any doubts, please let us know, since we are over the time. Otherwise, we will end. Any doubts in like whatever we discussed so far in today's session or in previous one or anything? So for the previous one, if I remember, somebody was asking me about inner product space, invariant inner product space, whether we can have T such that inner product space will be only trivial invariant vector subspaces are there. So in that case, we can take this, that T is equal to T from R2 to R2, just so that x comma y going to y comma minus x. Okay, so in that case, this is, so 0 is I mean, we proved already that V and R2, sorry, 0 and R2 will be invariant subspaces. This is true for any linear transformation. Okay, but so apart from, so this is two-dimensional vector space. So apart from 0 and 2, there are only one-dimensional vector spaces, and one-dimensional vector spaces will be of what form? Something of this form, right? C A comma B such that C is in R. So it is multiple of some vectors V. Okay, so it is like CV for non-zero V in R2. It is of this form. Or let me write this. A comma B in R2. Right, but T of W will be what? T of W will be T of this CV, which is C into, which is C into A comma minus B. Sorry, B comma minus A. And for this to be inside W, this is not possible, because if T of W or inside W, this implies that this C minus B, sorry, CB minus A is some D times A comma B. And this will not, and this is not true. You can check this. Okay, so this linear transformation gives that only possible invariant subspaces under this T are 0 space and V. Any non-trivial subspace which is one-dimensional subspaces in R2, they can never be invariant in this, under this linear transformation. Is this okay? I mean, the example was asked by, I think, someone in the last lecture. Okay, is it fine? I mean, those who are here, the question was, can we have a linear transformation such that only invariant subspaces are 0 or the whole space? So this is the linear transformation. where the only invariant subspaces are 0 and whole space. No non-trivial subspace, that is, in this case, will be one-dimensional subspace, will form a invariant subspace. That was the thing. And
Yes, ma'am. Okay,
yeah.
ma'am. Thank you.
Sorry, sir?
Thank you, ma'am.
Yeah,
Last week
sure.
I asked this question.
Okay. I hope this is okay now. If
Yes,
that
yes,
is
clear, ma'am. Clear, ma'am.
okay, sure. I mean, you can check this condition, okay? You need to check this condition that this will not happen. Yeah, but this is quite trivial that this won't happen. And so on. So, is it okay now that this is not this is example? And for today's lecture, if there is any doubt, please let me know. Otherwise, we can end the session. Yeah.
Ma'am, will there be class tomorrow?
Oh no, sir. It has been cancelled. Yeah. Only Saturday classes will be there. Yeah. For this week, I guess. Yeah. Any other doubt here?
Ma'am, tomorrow's class is cancelled only for this week or hereafter all weeks?
Okay, so that doubt is also for me. So even I don't know that. From the mail, I guess it was for this week, but I don't know. You can put that in the Google forum or the discussion forum or Google Classroom. The people will respond there. Yeah. Yeah.
Okay, ma'am.
Or if the lecture is next week, then you will receive the reminder for it as you receive for these sessions. Yeah. So okay. Any doubts now other than when is the tutorial? So for the Saturday tutorials will be there. So next week again on Saturday 3 to 5 p.m. Tutorial will be there. I'm not sure about the Sunday. Yeah. Okay. If there are no further doubts, I think we can end this session. Okay. Thank you.
Ma'am,
Yes.
our last exam, last proof, ma'am, you
Mm-hmm.
were given. Not this, ma'am, invariant subspace.
Okay. Oh, invariant subspace.
This three-dimensional case is not working.
Sorry, sir.
When we take R3.
So R3, there will at least be one invariant subspace in R3. So because see, why this is happening is because in this, if you try to write this as matrix, it is this matrix as far as I remember, or one of this or this, one of them it will be. And what will happen is these matrices are do not have any eigenvalues. So we have proved that eigenspaces always form invariant subspaces. So this matrices does not have any eigenvalue. That's why no eigenspaces. That's why no non-trivial non-trivial invariant subspace. But in R3, as far I mean, as soon as you go to R3, it would have there will be at least one eigenvalue in that case. And for that eigenvalue, we can have inner product space. So sorry, eigenspace, and that eigenspace would serve as invariant subspace, I guess. I mean, I don't know at this moment for R3, but
Yes,
I think
yes, R3 has every linear transformation is proper invariant subspaces.
yeah, exactly. That's what I was saying. Because in R3, the whatever I will get, the characteristic polynomial, it will have at least one root because it is 3-degree polynomial. So fundamental theorem of algebra and so on. So at least one real root will serve as eigenvalue, and
So odd power gives invariant proper invariant subspaces.
sorry, sir.
Odd dimension gives proper invariant subspaces.
Yeah, exactly. All dimensional should give proper invariant subspaces
Yeah.
because of this
Yes.
one non-zero, one real eigenvalue will give us eigenspace, which will give us invariant subspace.
That is fundamental theorem of algebra. At
Yeah,
least one
yeah.
real
Yes.
roads.
Yes.
Very,
One
very
real
nice, very nice.
Yeah.
And thank you.
Yeah. Sure,
Actually,
sure.
this is the last time NPTEL question,
Okay.
2023.
Sure. Okay.
I'm asking.
Sure. Okay,
thank
so I hope this is clear now. And
Yeah, very clear, ma'am. Thank you.
sure. So I think now there are no further questions. We can end the session for today. Yeah. Okay. See you next week. Thank you.